Welcome back, everyone. Let's just jump right into this explainer. Today, we're taking on a real beast of a geometry problem. Question 16 from the Pearson Edexcel GCSE Mathematics November 2023 paper 2H. If you're here, you probably love seeing how these giant puzzles get broken down into bite-sized, logical pieces, right? Well, you're in the exact right place. We're going to literally look under the hood and follow the exact mechanics of the examiner's mark scheme to crack this thing wide open. So, how exactly do we secure all 4 marks on question 16? That's the ultimate goal here. We're not just, guessing and hunting for the right answer. No way. We're going to acquire every single mark step by step using the exact logic laid out by the examiners themselves. Okay, first things first, let's get our bearings. The setup gives us a trapezium, ABCD, where side AD is parallel to side BC. We've got some crucial parameters to work with here. Side AB is 7.9 centimeters and BC is 15.3 centimeters. Then, looking at that top triangle, we've got angle BAD sitting at 112 degrees and angle ADB right at 42 degrees. Out of all this data, our mission is super clear. Calculate the area of the bottom triangle, BCD, correct to 1 decimal place. All right, moving right into process 1. Finding length BD. Now, to get the area of that bottom triangle, BCD, we quickly hit a wall. We just don't have enough info yet. We literally only know one side, BC. So the absolutely crucial first step, we've got to find the length of that shared internal diagonal line, BD, the one bridging the top and bottom triangles. That's our first major hurdle.
And boom, that brings us to our first official mark. The mark scheme explicitly states you get a process mark, a P1, for writing BD over sine 112 equals 7.9 over sine 42. This is a classic textbook application of the sine rule. If we look at the top triangle ABD, we just pair the side we want, BD, with the angle directly opposite it, which is 112 degrees. Then, we set that equal to the side we do know, 7.9, divided by the sine of the angle opposite that guy, which is 42 degrees. Just setting up this ratio, boom, you are on the board.
But we're not stopping there, right? The examiner wants to see that you can actually handle the algebra. So the second process mark, another P1, is handed out for a complete process to find BD. In plain English, that just means correctly rearranging your sine rule equation to get our missing side, BD, all by itself on one side of the equal sign. So how do we isolate BD? Simple. We just multiply both sides of our equation by sine 112. That leaves us with BD equals 7.9 divided by sine 42, all multiplied by sine 112. Actually, writing this explicit calculation down on your paper is exactly what locks in that second process mark. It proves to the examiner, without a doubt, that you have a clear mathematical path to the intermediate answer. Punch all that into your calculator, and you're going to get something like 10.946 and so on. Now, the examiners are actually pretty forgiving right here. The mark scheme specifically notes that values can be rounded or truncated at this intermediate stage. So honestly, whether you jot down 10.9, 10.95, or just keep that massive string of decimals saved in your calculator's memory, you've successfully bagged the first half of the marks for this whole problem. We've got our shared side. Okay, let's pivot to process 2, calculating the area. We've conquered the top triangle, so let's shift our focus downward to triangle BCD. We are finally ready for the main event, calculating the actual area, which, remember, is the whole point of question 16. To pull this off, we're bringing in the trigonometric area formula for a triangle. You know the one, half times side A times side B times the sine of the included angle C. The mark scheme hands out our third process mark, another P1, for essentially just plugging the right numbers into this formula. Specifically, they want to see 1/2 times your found value for BD times 15.3 times sine 42. Now hold on, where did that 42 degrees come from? Well, think back to the original setup. The top and bottom lines, AD and BC, are parallel. Because of the alternate interior angles rule, you might know it as the z-angle rule, angle ADB, which is 42 degrees, is exactly equal to angle DBC. So now, we've got our two sides, BD and BC, and that 42-degree angle squeezed perfectly right between them. Setting that up correctly, that's your third mark right there. We've done the heavy lifting. 3 marks down, 1 to go. Let's look at the final acceptable answers to see exactly how that last accuracy mark is awarded, because the examiners have some very specific variations they'll actually accept here. I actually love how rigorous the mark scheme is on this. First up, the A1 accuracy mark is given for any answer falling in the range of 56.0 to 56.1. It's a tiny window, but it allows for those minor differences depending on exactly when or how you rounded your intermediate value for BD. Second, there's this really fascinating special case mark, SCB2. Let's say a student completely butchered the area calculation, but somehow, out of nowhere, correctly found BD equals 10.9 without showing the proper steps for the first 2 marks. The examiner will still throw them 2 special case marks. Pretty generous, right? And finally, my absolute favorite safety net. Let's say you calculate the exact correct answer, right in that 56.0 to 56.1 range in your working space, but then you bizarrely round it wrong on the final answer line. The mark scheme dictates you still get full marks. They're testing your actual geometry skills, not penalizing a momentary brain freeze right at the finish line. And there it is, the moment of truth. 56.0 square centimeters. That's the perfectly rounded, baseline answer we've been hunting for. By just trusting the process, sine rule, a bit of algebraic rearrangement, alternate angles, and finally the trig area formula, we systematically built a bulletproof 4-mark answer.
So that is exactly how you crack question 16. When you follow this kind of step-by-step logic, calculating something like a complex area just becomes a highly structured, totally predictable process. It's like a giant puzzle where every piece just clicks. So, what do you think? What other complex exam problems should we deconstruct next? Keep up the awesome work, keep practicing those mark schemes, and I'll catch you in the next explainer.